Okay, so hello everyone. Welcome to the tutorial session for Introduction to Automata Languages and Computation. So, in this week, we will kind of summarize what everything that we saw throughout the week. So, it is more like a summarization. Okay, so yeah, so the last model that we saw was that of Turing machine. Okay, and yeah, and some of the other models that we came across throughout the course, I'm not listing all of them exhaustively, but just to capture, we saw what is called as a PDA, and we also saw what is a DFA or NFA and so on. So I'm not writing all of them, we will look into it in detail. But the point I want to make is that in this course, we sort of started with the simplest model, which is DFA. Then we went on to PDA, and then we went on we sort of started to realize that there is a limitation with DFA. Then we made the model a bit stronger. Then we went to the PDA, and then we defined what is called we saw there are limitations of the PDA on its own. Then we said then we defined the Turing machine, and we saw some examples for the same. So is it possible that there is something even beyond Turing machine? Is it possible that there is some language which a Turing machine is not able to capture, but maybe there is a machine which is stronger than Turing machine that uh, yeah, that might be there. So it turns out that in the 19th century, people asked this question in the so they asked, what is computable? Okay, so this was the basic question that they asked, in the sense that is it even possible that there are some functions that are not computable? So yeah, and this model was proposed independently by Church. Okay, so this is called Church Turing thesis, and what they say is that any algorithm that you can design, any algorithm that is possible to have, there is an equivalent Turing machine for the same, and vice versa. If you have a Turing machine, there is a corresponding algorithm for the same. So they kind of gave an equivalence of algorithms and Turing machines. And so we know that it turns out, we did not see in this course, but it turns out that there are functions that are beyond computation for Turing machines. And yeah, so we just live with that. So that then there is a whole theory that builds on top of that, but in this course, so it is beyond the scope of this course. But yeah, I just wanted to build in the perspective that this is how these models came up. So we asked a basic question that yeah, so we asked a basic question that are there functions that are not computable, or how do we know whether a function is computable or not? So to answer that, we built a theoretical model which is called a Turing machine, and Turing machines are as powerful as any computers that we have. So in the sense that any task you can imagine, there's an equivalent Turing machine for the same, and vice versa. So, in this course, we sort of started with defining what are DFAs, then we went to NFAs and other models within this, then we went to PDAs, and then we went to Turing machines. But that is not the order in which they came up. So, in fact, the order is reversed. So it so happened that we first came across this Turing machines model, and then we said, okay, what if the machine is not as powerful as what is given? What if the machine is restricted? So yeah, then what are the limits of computation? Okay, so here we did not define what restricted means, so we can put restrictions uh, on several parameters. So for if, just as an example, if we limit the memory to a stack, then we have what is called a PDA, push down automaton. And if you just make it memoryless, if you even remove that access to stack, then you have what is called as DFAs. And there are a lot of other models, intermediate. You can ask various questions and build models corresponding to it. So yeah, so that is the sense in which we studied these models. So yeah, so yeah, just with that build up, what we will do now is we will recall what is a DFA. So okay, so let's recall what is a DFA. DFA is defined as a 5 tuple. So this is, so here Q is the set of states, this is the input alphabet, then this is the transition function, then you have a start state, and then you have set of final states. Okay, so this delta is a function from Q cross sigma to Q. So what that means is that you have basically, let's take a simple example that we have seen in the course. So let's say you want to build an automaton for the language that accepts only odd numbers, and here let's say assume that W is in binary, or okay. Okay, so let's say we have a start state. Then the transition function tells us that if you are at a particular state and you see some symbol, then where do you go? So let's say on 0 you stay there, because we're not counting the number of zeros here. We are only interested in the count of ones. So then on 1, the parity becomes odd. So at this point you have seen even number of ones, and here let's say you have seen odd number of ones. Then if you see more zeros, then that is not going to affect the count of ones, so you stay there. But if you see another occurrence of one, then the count of ones as, um, if it were odd, then it has become even. So when do we accept? So notice that this state here captures the fact that the number of ones is even, and this state captures the fact that the number of ones is odd. So yeah, so this is what, so all these things that end in Q1 is what we want to accept. So this is how we defined the DFA model. This is a simple example for the same. Now suppose, um, yeah, yeah, now suppose you want to accept, just as another example, suppose you want to accept all W such that W is divisible by, let's say, 4. And by W we mean the binary, I mean W is given as binary. So let me write this, W in 0 1 star. And by divisible by 4, what do we mean? So for example, let's say the number that is given to you is 101. Then what is the decimal equivalent of this? So decimal equivalent of this is 5. And is 5 divisible by 4? 5 is not divisible by 4. So um, yeah, so the DFA should reject. But suppose the number that is the W that is given to us is this, then what is this number? this number is 8, and 8 is congruent to 0 mod 4 because 4 divides 8, so we should accept this. Okay, so the only point is that whenever you talk about w, we're talking about the decimal value of w, whether that is divisible by 4 or not. So how do we do this? So suppose the general idea is that we want to, okay, let me write this. The general idea is that we want a state that um, corresponds to remainder modulo 4. Okay, so if you divide any number, n is congruent to r mod 4, then what are the choices of r? R can be 0, r can be 1, it can be 2, or it can be 3. You cannot have that the remainder is 4, because in that case you can further divide the number by 4 and get a remainder of 0. So these are the only 4 possibilities. So for now, let's say these are the states corresponding to it. So let's say q0 is the state corresponding to this, q2 and q3 and so on. So yeah, so this is, let's say, q0, and what we are saying is that we are yet to read the string. So okay, so now what happens is, let's say you read a 0, so the w that is given to us is w1, w2 and so on up to wn. So the first thing that the first letter that we read, it can be 0 or it can be 1. So if that is 0, then the current remainder is 0, because 4 divides 0, so that's why you should stay in 0. But if the number is 1, then we know that 1 is congruent to 1 mod 4, so you should go to a state q1, which remembers that the current modulo, the current remainder is 1. Okay, so now you read the second letter. So let's say that the second letter is a 0. Okay, and yeah, yeah, then there are two choices. So if you are at q1, then what you read previously, you are at q1 because the symbol that you read earlier is congruent to 1 modulo 4, and now you are reading this 0. So what is the binary value of this? The binary value of this would be 2. So 2 is congruent to 2 mod 4. So yeah, we will go to a state q2 on reading 0 from here. But if you are at q1 and the symbol that you read is 1, then you have 1 1, and the binary equivalent of this is 3. So 3 is congruent to 3 mod 4. So from q1, if you see 1, then you should go to q3. Okay, so now we are done writing the transitions for q1. Now let's do the same for q2. Okay, so suppose you are at q2, and that means that your current remainder is 2, and let's say the next word, that the next letter that you read, suppose it is a 0, then what will happen is, let's say you had read a 1, and now you see a 0, then what that means is that your sorry, yeah, so suppose you had a 1 0 here, because 1 0 is nothing but 2, which is congruent to 2 mod 4, and let's say you see a 0 after this, then it is same as saying that it is same as shifting the whole binary word to the left. So what is the decimal equivalent of this? This is nothing but 4, which is congruent to 0 mod 4. So if you are at q2 and you see a 0, then you should go to q0. So this is what you have. And at the same time, if you have seen 10 but the letter that you see is a 1, then this number is 5 and this is congruent to 1 mod 4. So sorry, yeah, so then you should go to 1 from q2. And if you are at q3, then let's say you have read this, and if you see a 0, then the remainder is the number is 6, which is congruent to 2 mod 4. So you should go to q2. And if you were at q3 but you see a 1, then the number that you've seen is 7, which is congruent to 3 mod 4. So you should stay at q3 if you see a 1. So basically, the idea is that whenever you are at q2, let's say some qi, the current remainder that you have is I, and when you see one more letter, then the whole number is going to be pushed to the left. So it's as if the number it's multiplied by 2. So that's why we adjust the we adjust the states accordingly. So now the thing is, sorry, just a second. Okay, so now the idea is that we have written the states, we have written the transition functions, and the only thing that is yet to be defined is what is the set of final states. So in this case, we want to accept if a number is divisible by 4, and what we mean is we want to accept if the number is congruent to 0 mod 4, and which is the state that captures this. So it is q0 for us. So like we said earlier, q0 is the state that tells that the remainder is 0. So this should be an accept state for us, and nothing else should be accepting. So yeah, so this is the idea for DFA for the language L2. Instead of 4, if you had any number, any finite number k, then you would, using similar idea, you will be able to design a DFA for it using k states. So k is not optimal, but definitely there is a DFA with k states. So yeah, so that is one thing that we talked about. So we talked about what is a DFA model, and we saw some examples of it. Okay, so yeah, so then what, the next thing that we saw was what is called NFA. So okay, so NFAs are yeah, NFAs are the are models that are defined similarly, but the only difference is in the transition state. So this is again a 5 tuple. You have q sigma delta f q0. So everything is same. This is the set of this is the set of states, this is the input alphabet, this is your set of final states, and this is the start symbol. So everything else is the same, only that the transition function is defined differently. So here you have that this is a function from q cross sigma to 2 to the q. So this is the power set of q. So what that means intuitively is that if you are at a certain state, then on seeing a symbol, there are multiple possible branches where you can go to. So so it's basically non-deterministic in the sense that um, you are going to kind of simulate all of the paths for the given string, and if any one of the paths ends up in an accept state, then you accept it. So the acceptance condition is that x is in L if and only if there exists a branch in the computation tree that accepts X. So just as an example, suppose yeah, so okay, maybe I'll just take an example of a language. Yeah, so suppose L is the language of set of all strings such that W ends in 101. So suppose we want to draw a DFA for this, then what we will have to do is we have to adjust the transitions such that we guess where the end of the string is, because as we read the string we don't know where the end is, but what NFAs allow us to do is NFA allow us to guess that the end is that this is the end. So for example, if you have to draw an NFA, then you simply yeah, you simply do this and write 01 here. So notice that on the symbol 1 itself there are different two different transitions, that q0, so delta of q0 on 1, this is a set q0 comma q1, where there are two different transitions that are possible. So how do we know whether a string, let's say a string that is given to us is 0 0 1 1 0 1. So suppose this is the string that is given to us, and we want to check whether the given NFA is accepting it or not, then what we do is we draw what is called as a computation tree. Okay, so what is a computation tree? So it basically simulates every step, every possible branch. So you start at q0, then you see a 0 which is here, then the only transition that is possible is that you stay at q0, then you see the next 0 and the same thing happens. If you see another 0, then you stay at q0, then you see a 1, and on seeing a 1 there are two possible choices: either you go to q0 or you go to q1. So now we want to explore both of these branches independently. So now when you see a next one, then q0 again goes to two different branches, which is q0 and q1, and from q1 there is no path, because from q1 there is no transition that is defined on 1. So then this path will be pruned, so we will not explore this path further, because this is going to be rejected. So again there are two choices now, q0 and q1, and this is the next symbol that we are reading. So on 0, q0 stays at q0, so we are here, and q1 goes to new state, which is q2. So these are the two new states that we get now, and the last symbol that we read is 1. So q0 on 1 again has two choices. So q0 on 1 goes to q0, or it goes to q1, and q2 on 1 goes to q3. Okay, so at the end of this at the end, after reading this string x, there are three different states in which we can land up. So one is q0, one is q1, and the other is q3. So the states that we end up in is q0, q1, q3, and uh, q3 amongst this is the accept state. So if any one of the states that you end up in is accepting, then we accept. So x, which is 0 0 1 1 0 1, would be accepted. Okay, and let's take a non-example. So here we saw one example which the given NFA accepts. So let's see another example of the same kind. So I'll copy this diagram on the other page. Okay, so now let's see another example. So okay, sorry. Hmm. So let's see another example. So let's say x is 0 1 0 0 1 1. Okay, so this is a non-example. So what do I mean by non-example? So x is not in the given language because x does not end in 101. So our computation tree, no matter what, I mean, at the end, whichever state you land up in, none of those should be accepting. So let's see whether that happens. So you initially we are at q0. Yeah, so initially we are at q0 and then we see 1. So suppose you see a 1, then there are two choices: either you go to q0 or you go to q1. Then you see a 0, and from q0 you will end up in 0, and from q1 if you see a 0, then you go to q2. Now the next symbol to be read is a 0 again. So from q0 you stay at q0, and from q2 there is no transition that is defined. So if you are here, there is no transition that is defined if you see a 0. So this is going to be pruned. So we will not explore this branch because the transition is not defined. So now the next symbol to be read is a 1. So q0, if you from q0 if you see a 1, again there are two choices: either you go to q0 or you go to q1, and the next symbol that you read is a 1. So again q0 has two choices: one is q0, the other is q1, and from q1, as we can see, there is no transition that is defined on q1 on seeing a 1. So if you see a 1, there is no transition defined, so we will prune this. And there are only two states at the end. So we are done reading x, and there are only two states that we ended up in. So what are the two states that are reachable? That is q0 and q1. Now the question that we ask is, are any of these states accepting? So in this NFA, only q3 is the accept state, which is not in this set. Therefore x is x is going to be rejected by the NFA, which is consistent with what we wanted. So if it does not end in 101, then we looked at the computation tree, and uh, none of the branches that we explored ended up in an accept state. So we would end up simply rejecting this string. So yeah, that is about NFA. Now yeah, then we ask this question: is it true that NFAs are more powerful than DFAs? So why do we ask this question? Is because we know that NFAs have this extra capability, that if you are at a state, you can jump to several states simultaneously, whereas DFAs do not have that property. DFAs say that if you are at a state on seeing a particular symbol, there is a unique state in which you would end up in. So yeah, so that is why um, it is natural to ask, are NFAs more powerful? So it turns out that no, we saw a theorem that for any for an NFA n, there is an equivalent DFA such that the language of n, DFAM, such that the language of n is same as the language of m. So for any language for which you can give an NFA, there is an equivalent DFA for it, and DFAs are NFAs by definition. So it so happens that DFAs are equivalent to NFAs. So yeah, so this is the theorem that we saw, and we will not go into the proof of this, but we also saw a method of converting an NFA into a DFA, an equivalent DFA. So this is called subset construction method. Okay, so what do we do? What is the general intuition behind this? Okay, the intuition is that uh, yeah, so the intuition is that what we do is, from a given state, we write down all possible states that you can reach to on seeing a particular symbol. Okay, so maybe we will do an example. So let's take an NFA that we have drawn earlier. So we will draw an equivalent DFA for this example that we have. So let me get this example. Okay, so what is the idea? The idea is that you start at a, yeah, so you start at q0, and because that is your start state, and on seeing a symbol 0, what all states can be end up in? So from q0, if you see a 0, the only state you go to is q0, but from q0, if you see a 1, then you can go to q0 or q1. Similarly, if you are at now the next state that we will pick is q0 q1. Okay, so what do we write here? We write here everything that is reachable from q0 union everything that is reachable from q1. So from q0, if you see from q0, if you see 0, then you go to q0, but from q0, if you from q1, if you see a 0, then you go to q2. So the answer for us would be union of these two. So what we'll write here is q0 q2. Now similarly, instead of 0, if we saw a 1 here, if we would have seen a 1 from q0, then the states that you end up in is q0 q1, and from q1, if you see a 1, then there is no transition defined. So but what is the union of these states? It is q0 q1. Now the new state that we have obtained in this process is this state q0 q2. So we will write it on the LHS. So here you have q0 q2. Now yeah, So now we will do the same process for q0 q2. So delta of q0 on 0 is nothing but q0, and delta of q2 on 0 is not defined, so this is q0 for us. And we do the same process but for 1. So if you are at q0 and you see a 1, then q0 q1, and if you are at q2 and you see a 1, then you go to q3. So the union of this is q0 q1 q3. And what we do now is we have obtained a new state here, which is q0 q1 q3. So we will push this on the left hand side. So what you get here is q0 q1 q3, and yeah, okay. So now we will do the same. Yeah, so now we will do the same process for q0 q1 q3. So what I know is definitely q0 and q2 would be there, because I can simply use the values for q0 q1, and only thing I need to add is the delta of q3 on 0. So we know that q3 and on 0 doesn't go anywhere, so this is the same state. And similarly, I'll pull the values from 1. So by now you can probably see this faster than what we did earlier, so I'm simply writing this value here, and q3 on 1 again doesn't go anywhere, so this is what you get. So yeah, so notice that at this point, this state that we got q0 q2 is already on the left hand side, and this new state that we got q0 q1 is also on the left hand side. So we don't need to expand this process here further, because all the states that we could have reached is already here. So the whole idea here is that we are going to imagine these subsets as a new state. So imagine each of these subsets as a state and draw the diagram blindly. So let's say q0 here is the start state, then there is on 0 you go to q0, but on 1 you go to a new state which is q0 q1. So this is a new state for us. And from q0 q1, if you see a 0, then you go to a new state which is q0 q2, and if you see a 1, then you stay there. Then you are at q0 q2, and if you see a 0, you go back to q0. So this is the transition. And if you see a 1, then you go to a new state which is q0 q1 q3. So this is the new state. From this state, if you see a 0, then you go to q0 q2. So this is the transition. And if you see 1, then you go to q0 q1. So this is what you get. And what should be the final state here? So final state in the original automaton is only q3. So every state that has q3 in it should be final for us. So we look at each of the states. So this state does not contain q3, so this is non-final. Same for this one, q0 q1 and q0 q2, but this state contains q3 in it, so this would be a final state for us. If there were multiple states that contain q3, then all of them would be final states. So now let's see an example whether this is indeed the correct DFA. So let's take the same example. Let's say 0 0 1 0 1. Suppose this is x, then yeah, then what do we do? If yeah, you simply write the states that it is going to visit. So if you are at 0, then you will stay at q0. If you see another 0, you stay at q0. But from q0, if you see a 1, then you go to this state called q0 q1. From this state, if you see a 0, then you go to a state called q0 q2. And from this state, if you see a 1, then you go to a state called q0 q1 q2. So from here you go to q0 q1 q2, this state. and q3 the state, and this is a final state. So at the end of reading at the end, when you're done reading the string, if you reach at a final state, then x is accepted. So similarly, let's do one. Okay, maybe you can try this offline. So because we have limited time, okay, maybe let's just do one. So this one is accepted. Now let's do another example. So suppose x is 11000. Okay, suppose this is the x, and we know that this should not be accepted because it does not end in 101. So let's see how this works. So from q0, if you see a 1, then you go to the state q0 q1. So let me write that. So you go to q0 q1. From q0 q1, if you see a 1, you stay there. Then from here, if you see a 0, then you go to q0 q2. So this is the state q0 q2. And from here, if you see a 0, then you go to q0. So let's write that. So you have q0, and from q0, if you see a 0, then there is a self loop which takes you to q0. So again you go to q0, which is not an accept state. So at the end, you did not end up in the state q0 q1 q3, so you would end up rejecting it. This is what we wanted. So this is just to show that the DFA that we've designed indeed works. Then yeah, then the other model that we looked at, so I'll not go into the details of this, it is very similar. So there is something called epsilon transitions. So in this case, what happens is you are allowed to go to a state without reading a symbol. So let's say you are at some q, then if you write this, then what that means is that if you are at q and you haven't read anything, you can still reach p, because epsilon is zero length empty string. So that is an extra feature that this has. But it also again turns out that epsilon NFAs are as powerful as NFAs. So there is a easy method of converting an epsilon NFA into an NFA. So this is also something we saw, but it's not very hard to see, so I'll skip it for now. So this is another theorem that we saw in the course. So what we have so far is we have these models, DFAs, then we have NFAs, and then we have epsilon NFAs. Okay, so yeah, just a minute. Okay, so yeah, so the other model that we saw in the course, that is what is called a 2 DFA. And now the definition of a 2 DFA, so at that point it may have, if at all, it may have looked very I mean very non-intuitive. Now that you've seen Turing machine model, maybe this would make more sense, because this is exactly a Turing machine, but the only difference is that you're not allowed to write. So it's a read only Turing machine. So you have that, just like we defined for Turing machines, you have an infinite tape. Assume that it is infinite on the, it doesn't even matter actually whether it is infinite or not, because you are not allowed to write. So your input is written here, and this is the end of input, let's say. So it doesn't matter that the tape is infinite, because you can't write on it. So what happens is you have your header, which is pointing at some cell, and let's say this is 1 to n, and this is the state that you are in. And Yeah, and from here it tells you that if you are in this state and you are reading this symbol, then where you should go. But the only difference is that you can move right or left. So if you are at here and you see this symbol, you can move to the right or you can move to the left depending on the transition that is written. So a typical transition would look like, so you are at a queue and you see a symbol, then you should go to some queue, and you can move to the left or you can move to the right. So this is what a transition function for a 2 DFA would look like. So yeah, so this is the model that we saw. Now the advantage here uh, is that it kind of looks at first it looks more powerful because you can read and reread the input as many times as you want. So this is not the case with the DFAs or NFAs that we saw, because for DFAs and NFAs, at the end of the input, once you are done reading, you have to decide whether to accept or not depending on where you ended up in, which state you ended up finally. Whereas for 2 DFAs, uh, that is not the case. You can, once you are, let's say, done reading this, once you are done reading this, you can go back and forth and so on until you reach a special state. So how do we define the acceptance? So there is a special state called T and there's a special state called R. If you reach T, the moment you touch T, you are going to accept. So, and the moment you touch R, you're going to reject. So that is how we define the acceptance or rejectance of 2 DFA. And uh, yeah, similar to the models that similar to the models that we had earlier, it so happens that this is also equivalent. So we know that DFAs are equivalent to NFAs, these are equivalent to epsilon NFAs, and furthermore, they are equivalent to 2 DFAs. So the 2 here denotes it's a two-way DFA, because the header can move to the left or right, um, in both the directions, whereas for the other models you just kept on moving to right, which is one direction. So it so happens that this model is also as powerful as the DFA or the other models that we have. So um, yeah, yeah, so that is one thing that we saw in the course. And why do we need the 2 DFA model? So it so happens that sometimes it's more intuitive to design a 2 DFA. It may be a little challenging to make a DFA, but it may be easy to make a 2 DFA for it. So then in that case, what you can do is you can design a 2 DFA for it and convert it into a DFA using standard techniques that we have. So that is sorry. Sorry, I need to share the screen again, so just a second. Okay, so yeah, so this is what we have, and these are the some of the models that we came across. Then we know that so I'll, maybe in interest of time, I'll not do an example for 2 DFA right now, but at the end of the tutorial, if there is some more time, then I'll try to take up some example. So then we said that the languages that DFAs can recognize, or equivalently any of the models that we saw can recognize, these are called regular, we call them regular languages. So L is regular if there exists a DFA such that the language of M is equal to L. So yeah, so these are the regular languages. So let me write here. So yeah, so this is power set of sigma star, meaning this is the set of all the languages. So this rectangle here is set of all possible languages that can be there, and this set that I am drawing, this is the set of regular languages. Okay, so the natural question that comes up is, uh, are there languages outside this? So is it possible that there is something outside here which cannot be pulled in inside? So this is a natural question that arises. So question is, the next curious question that we ask is, um, are there languages that cannot be recognized by DFAs? And the answer for that is affirmative. So it turns out that the the DFAs are not all powerful, so there are languages here. So one example, that the first example that we saw yeah, the first example that we saw here is 0 to the n, 1 to the n for n greater than equal to 0. So we saw that this is a non-regular language. And how do we show that? So how do we show that something is regular? um, yeah, so how do we show that a given language L is regular? So just simply give a DFA. Or any equivalent machine. But how do we show that L is not regular? Okay, so the challenge here is that for showing that a language is regular, you can simply give a DFA. But if you want to show it is not regular, what we want to say is there does not exist a DFA which recognizes L, or in other words, this same as saying that for every machine M, which is every DFA M, we have that L of M is not equal to the given L. So how do we go across all M? Because how many DFAs can be there? There can be infinitely many DFAs. So these are infinitely many. So we are not happy with this because we can't. If I want to show you that it is not possible to give a DFA, I don't want to run till infinity, because I'll never be able to. I'll just keep running till infinity if there is no such machine, and I'll never be able to stop and tell you that there is no such DFA for the language. So this is the difficulty in proving impossibility result. So this is the first kind of impossibility result that we saw. And generally, to show impossibility results, we need to look for something more creative. So in this case, the solution that we use is what is called a pumping lemma. Okay, so what does the pumping lemma say? The pumping lemma says that it says that there is a certain property of regular languages. So if L is regular, then something happens. And if you want to show that something is not regular, you will show that the property is not true. So the pumping lemma says that if L is regular, then there exists a pumping length, let's say n, such that, so notice that the pumping lemma is applicable for infinite languages only, because if the language is finite, then you can always give a DFA for it. So as an exercise, maybe you can try this. If L is finite, then L is regular. So try to prove this. Maybe we might have seen this example in one of the tutorials, but yeah, this is still a good example to try. So that basically tells why pumping lemma is applicable for infinite languages only. So yeah, so what do we do? So okay, yeah, so what we do is we say that if a language is regular, then there exists a pumping length n such that for all strings x in L whose length is at least n, we can write x as uvw. This is u concatenated with v concatenated with w, such that first property is that the length of v is um, yeah, is at least 1, and the second property is that um, yeah, then the second thing that we say is that if yeah, the second thing that we say is that you if you pump it u v to the I w will be in the language for all I greater than equal to 0. So there is a certain string such that yeah, there's a certain string that if you keep on pumping it over and over again, then the resultant string will always end up in the language. So just as an example, yeah, so it makes more sense to show that a language is not regular using pumping lemma. So let's do one simple exercise. So let's take the same example, 0 to the n, 1 to the n. um, so let's say that the pumping length that we are using is n. So we will show that, let's say x is 0 to the n, 1 to the n. We want to show that no matter how you write this, so if you write this as uvw, no matter how you write this, the resultant string would not end up in the language. So suppose there are cases. So suppose that um, yeah, so suppose that v consists of zeros only. In that case, u v to the iw would be uh, so suppose u is 0 to the k, v is 0 to the n minus k, and okay, maybe let's do it other way around. This is 0 to the n minus k, this is 0 to the k, and w is 1 to the n. So uh, so in particular u v square w, this would be 0 to the n minus k, 0 to the 2k, 1 to the n, which is 0 to the n plus k, 1 to the n, but k is greater than equal to 1. So we know that the number of zeros and ones here does not match, so hence u v square w is not in the language. So case 1 is already ruled out. Similarly, if you do case 2, so case 2 would be that v consists of only ones, then you end up getting more ones than zeros. So you will end up getting something like 0 to the n, 1 to the n plus k. uh, okay, so this is what you end up getting, and again this is not in the language. So um, yeah, so the third case that can happen is maybe that these are the several zeros, these are several ones, maybe u is somewhere here, v is somewhere here, u is here, and w is here. So maybe it contains some several zeros and ones together. So suppose that is the case, then u is some 0 to the n minus k, v is 0 to the k, 1 to the l, and w is 1 to the n minus l. Now what happens if we do u v square w? Then you get 0 to the n minus k, 0 to the k, 1 to the l, 0 to the k, 1 to the l, followed by 1 to the n minus l. So in this case, you basically have a block of zeros, then you have several ones, then you have a block of zeros, and then you have a block of ones. So this is not at all the structure of the strings that we are looking for. The strings that we are looking for are of the form 0 to the n, 1 to the n. So there is a block of n zeros, there is a block of 1 n's. We are not looking for structures where you have some zeros, then some ones, then some zeros and some ones. So this is clearly not in the language. So what we saw is there are only three possible splittings of UVW, and in any of the possible splittings, these are the three cases that we saw. So in any of the cases, we saw that the string resultant string is not in the language, therefore L is not regular. So this is what we so this is what we proved. And the proof of pumping lemma is also something that is very a very neat and beautiful argument. So it basically relies on simple counting, which is pigeonhole principle. So it's a simple observation, so it's worth looking at it, but in interest of time we'll not look into it. But yeah, I think it's still a nice argument to take a look at. So yeah, so what does the picture look like? um Sorry. Yeah, so yeah, just a second. Yeah, so so that was one example of the pumping lemma. So what we just saw is that this is the set of all all possible languages, and this is okay. So this is where our regular languages lie, and we saw that there is a language here. Okay, so um, so then what we will see is that if you make the model a little bit more powerful, then there is a class of languages that we can recognize. So this is what we call the context free languages. And so I'll get into it, but before that I just want to mention another important thing that we saw about the regular languages. So we saw what is called closure properties of regular languages. Okay, so the closure properties that the simple questions we asked is if L1 is L1 L2 are regular, then what can you say about L1 union L2? So it so happens that L1 union L2 are also regular, and it happens that L1 intersection L2 is also regular. The complement is it is also closed under complementation. It is also closed under the clean star operation, and it is also closed under the reversals. So to see the reversals argument, we can um, use the NFAs. So it is simpler to argue with NFAs, but mm, yeah, sorry. So this is something we've done in the previous tutorials, but just one statement that I want to say about this is if you want to see that it is closed under complementation, then what you do is we just swap the accept and reject state. So just by this just by swapping the reject and accept sets, you can get a DFA for the complement of the language. But how do we do this? For doing this, we used what is called a product construction. So I will not get into the details of this, but this is definitely worth taking a look at. For showing clean start, we relied on epsilon NFS. In fact, for all of them, it's kind of useful to think of it in terms of epsilon NFS. But yeah, you can do it without it also, just that it may be slightly more complicated. So we saw what is called a product construction. So what you do is you have two machines, two DFAs, and how do we merge them together so that it recognizes the language that we want. So this is something we saw, but there is another way of seeing that the regular languages are closed under these operations, which is using what is called a regular expression. So I'll just say a few words about regular expression. So yeah, how did we define regular expression? It was a inductive argument. So we said that any element a in sigma is a regular expression, and epsilon is also a regular expression. And then we said that if r1 and r2 are regular expressions, then so is r1 union r2, uh, or this is also written as r1 plus r2, and so is r1 concatenated with r2, and so is r1 star, and so is r1 complement. So okay, we don't have notion of complements. Okay, just a second. Yeah, so based on these inductive properties, everything that you can build up using these rules is what is a regular expression. So just based on this um, just based on this definition, what you have is, suppose, okay, so maybe I'll get a new page. So there is a one step application of this idea of regular expression. So we know that regular expressions is exactly same as DFAs. This is exactly what NFAs capture, this is exactly what epsilon NFAs capture, and this is exactly what 2 DFAs capture. So we have this entire chain of equivalences. Yeah, so this is the entire chain of equivalence that we have. And now if you want to show that regular languages are closed under union, let's say, so suppose L1 and L2 are regular, then there is some regular expression r1 for L1 and there is some expression r2 for L2. So if we write r1 plus r2, then this is a regular expression corresponding to the language L1 union L2. And similarly, if you write r1 concatenated with r2, then this is the regular expression for language L1 concatenated with L2. So for complementation and for intersection, it is a bit non-trivial to get a regular expression directly. So if you want a regular expression, then maybe you can get a product construction for the intersection language and convert it into a regular expression. So we have seen this. If you have a DFA or if you have an NFA, then there is a way of obtaining a regular expression for it. And similarly, if you have a regular expression, then we have a step-by-step procedure to obtain a DFA for it. So at the moment we will not get into the details, but yeah, there is a step-by-step procedure for, in fact, for any two models that you pick here, there is a way to convert one model into the other and vice versa. So that is what we mean by equivalence. And yeah, so with that, I'll stop the discussion for the regular languages, and we will talk a little bit about the next model that we introduced. So we know that DFAs are good. DFAs are very simple models that are capable of recognizing languages, but there are languages, like we saw, which cannot be recognized by DFA. So there are limitations of DFAs, and that's why we ask, okay, is there a model which is slightly more powerful than DFA, but it can recognize the languages that we want? So then we propose what is called context free, or let's say, let's start with the models. So this is push down automaton. Okay, so yeah, so what do we mean by push down automaton um, is that you have an additional stack. So there is a stack, and initially the symbol in the stack is Z, and you can go on pushing and pushing on the top of the stack, and you can pop out of the stack. So push and pop on the top of the stack. So these are the two operations that you are allowed. Everything else that is done is similar to what DFA does. So you basically have a, yeah, so you basically have a bunch of states, and you can go from one state to the other. And the only thing that is additionally being done is that what do you do on the stack? Do you push an element or do you pop an element? That's the only thing. And we saw two kinds of acceptance conditions. So we saw acceptance conditions. It turns out that these are equivalent. So we saw acceptance by empty stack, and the other is acceptance by empty string. So what do we mean by acceptance by empty stack? It means that if you are done reading the string, and the so this is the string that you have, and you are done reading the string, and at that point your stack is empty, then we are going to accept no matter what state you are in. So it doesn't matter, irrespective of what state you are in, if the stack is empty, you accept. What do we mean by acceptance by empty string? It means that you are done reading the input, and there may be some content here on the top of the stack, it does not matter. But if you have reached the final state while you are done reading the string, then you're going to accept no matter what is there on the top of the stack. So it turns out that these two conditions are equivalent, and so it's enough to design a PDA with acceptance by empty stack condition or the other one. So let's do one example. Okay, so let's do one example. So let's take the favorite language that we have. Suppose we want to get a PDA for this. So what we do is, the informal idea would be that first you if you see zeros, then keep pushing. Okay, but if you see a 1, if you encounter a 1, then pop a 0 from the top. So what that means is that initially you saw some n many zeros and you pushed all of them. Now you are going to see n many ones. So for each one you see, we are going to pop a 0. So if you see n ones, then we would have emptied the stack. So that is the idea. So if string is empty and the stack is empty, then accept. So the acceptance condition that we are stating here is what is acceptance by empty stack. But it also so happens that this also works for acceptance. The same automaton that we will draw also works for the other condition. So what does that look like? So you start at a state q0, and if you see, initially the top of the stack is set. If you see a 0, then we just want to push the 0 on the top of the stack. Similarly, if you see more zeros, then you just, and the top, even if the top of the stack is 0, then you just want to keep pushing. But let's say you see a 1 now. So on seeing a 1, let's say we just want to um, yeah, we just want to empty it. So we will pop it. If you see a 0, we are going to pop it, and we go to a new state q1. And if you keep on seeing more ones, then we are going to pop the zeros. Okay, so this is what happens ultimately. If yeah, ultimately, if there is nothing to see and you have reached z, um yeah, then you pop that as well. And you go to an accept state, let's call it accept. And then you end up, you stay there. So that is a simple PDA for the given language. And yeah, so as we can see in the diagram itself, it's the same as TFS. The only thing that is additional here is this factor: are we pushing or are we popping? So that is something that is extra that we need to write. But the language that DFA could not recognize, so we saw using pumping lemma that 0 to the n, 1 to the n is not regular, but we saw a PDA that recognizes this. So definitely PDAs are more powerful than DFAs. So yeah, so maybe I'll write it here. So we know that the languages that are recognized by PDAs are called context free languages, or CFLs. So by the PDA, when we say PDA, by definition we mean that this is non-deterministic. But if it is deterministic, then we specify that it is deterministic. So what do we mean by deterministic and non-deterministic? Here is again the same idea or the same notion as we have for DFA. So what that means is, from in case of non-determinism, you can have multiple choices that a PDA can do. So if you are at state q0 and you see a 0, then maybe there are lots of choices that you can do. Either you can go to some state q4 and push a symbol there, or you can go to a state q3 and pop a symbol there. So there are lots of branches that could be there. So that is what we mean by non-deterministic. And as in case of TFA, we have that the non-deterministic and the deterministic versions are equally powerful, but that is not the case for PDAs. So it turns out that non-deterministic PDAs are, so this is simply PDA, are strictly more powerful than the deterministic PDAs. Okay, so this is something that is different from how it was for the case of DFAs. And yeah, and so let me just define the context free languages. So there is something called as context free grammars. That is another way of looking at a CFL. So these are called CFGs. And any of the programming languages, all the programming languages are examples of CFGs. And yeah, so in fact, the term grammar here is it's itself inspired by the grammar in the literature, the English literature that we have, because it is very similar. And we also saw some examples in the previous tutorial. So it is in a similar spirit that we call it a grammar. And so yeah, why is it called context free? There is something called context sensitive grammar. So this is not something we saw in the course, but I just want to give you an idea of what is there outside which we haven't seen. So what context sensitive, like the name suggests, is that if you have productions of the kind that A gives, if you have read something here, let's say if you have read some condition here, then you write something, and if you have read something else here, then you write some other production. So this is because, so this part here is what tells you the context. So hence it's called context sensitive. But the grammars that we saw looked something like A gives B, B, or C or something. So here you don't have any context. It is independent of what context it is. If you have this variable, then it will give you one of the production. So that's why this is called context free grammar. So just wanted to give you an intuition of why it is called context free. So how did we define this? This was defined as a four tuple. So you have a set of variables, you have a start variable, you have set of rules, and uh, you have non-terminals and terminals. So this is the start variable, and this is the productions. So let's do one example. So let's stick to the example that we have been doing. So L is 0 to the n, 1 to the n, where n is greater than equal to 0. So how do we give a grammar for this? So let's say S gives you so the idea is that we saw what is called parse tree or a derivation tree. So what it does is, from the start symbol S, it looks at a production and keeps on building it from top to down. So suppose I write this, then what this will do is it will replace the start symbol S with one of the rules. So this is what you have. And let's say further you have one more variable here, so I mean, since I have only one rule at this point, it will just keep on doing this. So it will have several number of zeros to the left, and it will have generated several number of ones to the right, and the number of zeros and number of ones here would be equal, because for every zero that an S gives, so for every zero that an S gives, there is a one that it generates at the right. So hence the number of zeros and ones would end up being the same. And what the CFJ insists is that you have to terminate every variable at the end into some non-terminal. So let's say I add one more rule here, that S gives epsilon. So then this would always generate strings of the form 0 to the n, 1 to the n greater than equal to 0. But if I want a language, let's say 0 to the n, 1 to the n plus 1 for n greater than equal to 0, then I can simply modify the grammar slightly by saying that S gives 0s1 or 1. So these are the kinds of examples that we looked at. You can simply tweak your grammar slightly and uh, get the corresponding language. So there are two different derivations that we saw. So one is what is called leftmost derivation, and the other is what is called the rightmost derivation. So in the leftmost derivation, what happens is that is that you have this derivation tree, and let's say um, yeah, so let's say these are the kinds of symbols in the tree. Then you have two choices at this point. Either you can expand a or you can expand b, but what leftmost derivation says is that you are always going to pick up the leftmost variable and you're going to expand that. So then you will maybe yeah, maybe you will expand on a, and then again you have two variables at this point. This both are b, but again you will choose to expand this b, the leftmost b first, and keep on doing this. Whereas if it were the rightmost derivation, then this is the one that we would have expanded first, and so on. So it turns out that these are equivalent. So for any string, if you have a leftmost derivation, you can also have a rightmost derivation. So uh, these are equivalent in that sense. But one thing that we particularly noted here is what is called ambiguous grammar. So what we said is, if okay, so this is what we said. So for if in the grammar that you have designed, if it is possible that there are two different leftmost derivations for a particular string, then you say that it is ambiguous. And it is sometimes possible um, to remove the ambiguity. So from a given ambiguous grammar, we can convert it into an unambiguous one, but it is not always possible. In such cases, we say that the language itself is ambiguous. So this is also something we saw. And so yeah, so the picture that we have so far looks like this. So you have regular languages, then you have CFLs, and you have 0 to the n, 1 to the n here, and this language here. And yeah, the question that we have is again the same as what we asked earlier. Are there languages here sitting outside? So is it possible that there are languages that even a PDA cannot recognize? So we ask the same question. So okay, so this is the question that we have. And again the answer to that is yes. So again, how do we show that? So if you want to show that a language is context free, then either you give a grammar for it, either you give a CFG for it, or you give a PDA for it. But if you want to show that a language is not context free, then what you do is you have again the same solution that we had earlier. You have what is called a pumping lemma, but this time the pumping lemma that we have is for the context free, or I mean it's for the context free language. So this is somewhat different. The intuition and the spirit behind it is the same, but the way it is stated and the conditions that are there are somewhat more sophisticated than that for the regular languages. So what does the pumping lemma say? That it says that if L is a is a context free language, then for any string x, which is okay, maybe I'll call it any string s which is in the language L, whose length is at least n. So this is again, let's say, a pumping length for us. So in case of regular languages also, we had what is called a pumping length. Here also we have what is called a pumping length. So what we say is that there is a there is a way you can write this as. So you can write, there is uh, exist u v w x y such that s can be written as u v w x y. This is the concatenation of the strings. They satisfy, first condition is that vwx is at most n, and um, and the length of vx, sorry, yeah, the length of vx is at least 1. Then if these two conditions are satisfied, then for all I greater than equal to 0, you have that u v to the I w x to the I y. This is in the language. So this is what the context free language basically, this is what the pumping lemma for this is. So as you can see, in case of the regular languages, we didn't have this two chunks that are going to be pumped up or pumped down. um, yeah. So in case of PDAs, however, we have this thing. So let's look at one example. So let's show that L, which is 0 to the n, 1 to the n, 2 to the n for n at least 0, is not a context free language. So how do we show this? Okay, so how do we show this then? uh, um, let's apply the pumping lemma. The idea is that we are going to take this string s is 0 to the n, 1 to the n, 2 to the n, and let's say n is the pumping length for us. And what we say is that you are going to break this no matter how you break this into u v w x y. For every possible break, every possible concatenation, or every possible distribution of s, if you pump u v to the I w x to the I y, you will never get a string in the language. So we will go for all cases. So we know that length of vwx is at most n. So let's see how this works. So there is a chunk of zeros, there is a chunk of ones, there is a chunk of twos. Now suppose that vwx is entirely contained here. So suppose vwx is some string of zeros, then if you pump u v to the I w x to the I y, then the number of zeros, if let's say suppose I is equal to 2. Okay, so then you get 0 to the m, 1 to the n, 2 to the n, where m is strictly more than n. So you will end up getting more zeros on the left because we are pumping up the string. So this is something that we yeah, that we do not um, yeah, this is something that we do not want. So this would not be in the language, because simply because of the definition, because it has to have equal number of zeros, ones and twos. And the other two cases when vwx is 1 to the k or 2 to the k can be handled similarly. This is because it's the same argument. In the, let's say it is a chunk of ones, then you get a string like 0 to the n, 1 to the m, 2 to the n, where m is more than n. So and for twos you end up getting more number of twos. So in either case you get a contradiction. Okay, now the other case that we want to handle, which is slightly different from this one, is that you have a bunch of zeros, then you have a bunch of ones, then you have a bunch of twos, and let's say that your uvw chunk is here. So notice that it is never possible that it has all possible strings. It can't have zeros, ones and twos at the same time, because if it has to have ones, then it will have to have at least 10 many ones, and the length of UVW is bounded by n, so it can never happen that you started at 0 and your UVW ended at 2. So this is simply not possible, so this case does not arise. And so you have bunch of zeros followed by a bunch of ones. So now suppose we pump up, then what you get is uv square wx uvx square, sorry, vwx. Yeah. So why, what this would look like is that there would be a bunch of zeros that were already there, then you have zeros followed by ones, and because this string was this vwx is pumped again, then you get few more zeros, few more ones, then the ones that were already there, which is this part and this part. So let me write this. So this is one occurrence of vwx, and this is another occurrence of vwx because we pumped it. Sorry, this is not what it looks like. Okay, so then what it looks like is that you have some zeros here, then you have, yeah, you'll end up getting few more zeros here and few more ones here. So this will look like 0 to the m followed by 1 to the k, 1 to the L followed by 2 to the n, where m and l are strictly more than n, because either m is more than n or l is more than n, because what would happen is either we are pumping up the zeros, or we are pumping up the ones, or we are pumping up both, but at least one of zeros or ones are going to be pumped up, but the number of twos are untouched. So number of twos is still n, but we are increasing the number of zeros, or we are increasing the number of ones at least. So that's why we would end up getting a string which is not of the form that we wanted, then this string is not in the language. And the other case where vwx lies here, so it contains few ones and few twos rather than few zeros followed by few ones, is very similar. It is symmetric and the same argument works for it. So this is how we show that. So without loss of generality, there are only two cases. One is where it lies vw x lies within a chunk of zeros or ones or twos, or it is interspersed, but in either case we end up getting a string which is not in the language. So we conclude that this language is not context free. And just a few more words about this. So we have yeah, so now we have regular languages here, we have CFLs here, and now we know there are languages outside. Okay, and this is the set of all languages. And then again the question that we ask is there a more powerful model that we can have? Uh, so then we show that there is yet more powerful model which is called Turing machine, and the languages that it can decide is what is called decidable. And there's a further set that is called recursively enumerable. We will talk about this, but few more words about context free languages is the properties, the closure properties of CFLs. So we ask the same question: if L1 and L2 are CFLs, then what can we say about L1 union L2? It so happens, yes, context these are context free. Then if you do L1 concatenation with L2, this is also context free. If you do L1 star, this is also context free. But if you do a complementation, then it turns out that this is not closed under complementation, and similarly it is not closed under intersection. It is not closed under intersection. Okay, so this is what we have. And This is again in contrast to what we saw for regular languages. For regular languages, it was closed under all the five properties that we mentioned. So, okay, just to make a fair comparison, so it is also closed under reversals. This is reversal. So this is again similar to what we have for regular languages, but these are the only two differences that we have seen so far, that does not match with that for the regular languages. And yeah, so this is a good enough recap for the context free languages. And in the next 5 minutes I will just talk about the Turing machine model. I may not get time to do an example, but let me just recall the definition. So then we say that, okay, is there a stronger model, and that is what we call the Turing machine model. Okay, so what does a Turing machine do? It is a 7 tuple. So you have q, sigma, then you have a transition function, then you have your accept state, you have a reject state, then you have your tape alphabet, and you have yeah. So what am I missing? Yeah, you have the start symbol, the start state. So this is how we define the model. This is your tape alphabet. And what we say is that the model is as follows: you have you have a work tip here, you have yeah, this is your left hand marker. So we are assuming that this is infinite to the right, this is infinite, one way infinite tape. And you have your input or something that is written on this tape. And what we do is, and then the rest of it is just blank symbol. So this is a special symbol that says that there is nothing written on the tape. So what we do is, if you are at a particular state, this is the header, this is finite control, or it's also called head. So it is pointing at a certain position or a certain cell. What we say is that if you read a symbol, and if you at a particular state, and if you see a particular symbol, then you should go to a certain state, you should write something um, on that cell, and you should go to the left or right. So this is similar to the 2 DFAs, but the only change is that you are allowed to write, whereas in case of the 2 DFAs you did not have a luxury of writing this part. This gamma part was not there, it was just a q cross l or r. So you just read, you made your transition, and you moved to the left or right. So that was the thing for 2 DFAs, whereas for Turing machines you have this. So um, we will do just one example, one very high level example. So let's take the same language. L is 0 to the n, 1 to the n, 2 to the n greater than equal to 0. And we know that this language is not context free. So what we will show is there is a Turing machine for this. So what is the idea? The informal idea, high level idea, is that you yeah. Yeah, so the high level idea is that what you do is, first of all you check that, you do a sanity check that the input is of the form 0 to the m, 1 to the n, 2, or let's say 0 star, 1 star, 2 star. So basically what we want to do is, we want to make sure that input is indeed zeros followed by ones followed by twos, and it is not that there are some zeros, then there are some twos, and so on. So if there are these kinds of input, then we will straight away reject. So this is what we do. So how do we do that? You have this tape, you go read, start from zeros, keep on reading the zeros. If you see a 1, make a transition, and just go keep on scanning to the right until you are done reading ones. If you see a 2, then keep on scanning till you're done seeing all the 2s, and if you see a blank, then return all the way back. So this is the simple idea for executing a sanity check. Then once you are done, you know that it is of this form. You just want to make sure that number of zeros is same as number of ones, it is same as number of twos. So what you do is you uh, read a 0 and mark it with A, then uh, find first one to the right and mark it as B and move back. Okay, so what that means is, if you have bunch of zeros here and bunch of ones here, what we are going to do is we are going to if this is the first 0, we will write this as A, then everything else is 0. You see the first one, write this as B, and everything else is 1. And once we are done doing this, we will come all the way back, find the first 0, make it an A, go all the way back, make the second occurrence B. So at the end, what will happen is, if there are any number of zeros or number of ones is exhausted, then reject. Then that means that, because then number of zeros was not equal to the number of ones, so at that point we reject. Otherwise otherwise uh, find the first occurrence of B and make it a 1, go to the right, find the first occurrence of C and make it a 2, of 2, make it C and go back and repeat the process. So at this point, we are basically checking whether the number of ones is equal to the number of twos. But number of ones are already, all the b's are replaced with ones are replaced with b's. So we want to check that the number of b's is equal to the number of twos. So we are doing the same idea, but if you exhaust number of, if supply of b's or twos is exhausted, then reject, else you accept. So this is the simple high level idea. So what we are doing is, we are first checking that the input is of the form 0 star 1 star 2 star. If that is convinced, then we are checking that number of zeros is equal to number of twos. So how do we do that? For every 0 we make it a, for every 1 we make it a b. If at any point now the zeros or ones are exhausted, then you reject. Otherwise we are going to check for number of ones and number of twos. So this is the same idea. So for every b you make it a 1, for every 2 we make it a c. If any of the b's or 2's are exhausted, then you reject, otherwise we are going to accept. So this is the simple high level description of the automaton, and we can also design a Turing machine for the same. So yeah, so what we did today is we recalled all the yeah, we recalled all the models that we saw, all the entire hierarchy of languages: regular languages, context free languages, and the decidable or the and the Turing recognizable languages. So we also saw some impossibility results which is for both of them we have pumping lemma. For Turing machines we have to do a little more effort, and it is not very trivial, and it's also not a part of the course. But there is a view, there is a world outside the Turing machines that is also that's also there, but it's not a part of this course. So uh, just wanted to bring it up. So yeah, I think that is all I wanted to discuss. Yeah, so all the best for your exams, and I hope the session was useful. So I think I'll stop the recording now. Okay, so thank you.